Hello, my name is Michael. We are team number 14. I'm joined today with Mario and Sebastian. The purpose of our project was to do a slider crank mechanism analyzation and animation. The slider crank mechanism we had to calculate two closures using the position, velocity, and acceleration analysis. Later then carry these calculations into a simulation showing that we have full rotation with no interruption, and as well validating our calculations, matching them with our simulation.
For the second part, we needed to synthesize a 4-bar mechanism. To do this, we had to create a 4-bar mechanism that had a coupler move through the 3 given positions. And with this, we were able to design a simulation that proved that we had fluid flow.
The motivation behind the slider crank mechanism came by with the internal combustion engines. It's a great common example of a slider crank mechanism. The slider crank mechanism exhibits both a linear and rotational motion. As you can see here, we have a linear motion of the piston head, which later translates towards the crankshaft that gives the rotational input that later transfers to the transmission and later throughout the whole powertrain of the vehicle.
In the design of an RC car, I noticed that a great example of a double 4-bar mechanism was the steering system. As you can see, you have the rotational input of the steering wheel, and that gives you the rotational input of the coupler link.
The divisional responsibilities are as follows. I took responsibility of the slider crank mechanisms, calculation, and animation as well as the report portion of the slider crank mechanism. Sebastian took the responsibilities of the 4-bar mechanisms, calculation, and acceleration. The report portion of the 4-bar mechanism was divided in between both Mario and Sebastian, as well as Mario took responsibility of the researching both slider crank and 4-bar mechanisms, and we all took part in participating for the PowerPoint presentation.
A brief history of the 4-bar mechanism. Archimedes was the first to apply geometry to lever designs, and Da Vinci was the first to actually put them into practice. He took the rotational input from a user and converted it into a straight line motion as a hand mill. The industry is something that has greatly benefited from these 4-bar mechanism, whether it be construction, automotive, or anything. A perfect example on the right is the backhoe. It has reduced a lot of production costs in the construction industry, and 4-bar mechanisms as a whole have made the processes more efficient. A slider crank is a special case of the 4-bar mechanism, dating back as far as the 3rd century AD, in which a sawmill on the right converted the rotational input into a linear output of the saws. This was later translated into the textile applications when it came down to fabric making or punch presses in manufacturing. There are 2 types, inline and offset. Inline being that the line of displacement is in center with the crank center, and offset is exactly as stated. It is offset either by an angle or some displacement. Some common applications of either a 4-bar or a slider crank are suspension components, either car or bicycle, or the pantograph, which was used to scale drawings. And the slider crank, as we chose for our application of this project, is the crank and piston assembly, and even the aviation industry is using it for flap designs. Opportunities for new designs are endless. Every industry benefits, whether it's the construction, aviation, even the classroom or educational industry. A recent application is the car. It went from a counterlever design over to a 4-bar mechanism, which increased the trunk space that the end user had, and it helped with production costs. And future development can be as simple as increasing space in toolboxes for medical applications, and can be as complex as a amputation, a prosthetic robotic design, which would give the user a more human-like feel.
The slider crank mechanism analyzation and animation portion of the project are as follows. We were given certain parameters such as R1, R3, R4, as well as the length of the point attached on the coupler, which is denoted by QS. And we were also given the velocity and acceleration of the actual link length R, which in turn ended up being our input value. The chosen parameters that I chose were as follows: the R2 crank length, as well as theta 1 and theta 4. I chose these at my own discretion, as stated, and was done so that the linear motion and full crank rotation motion was interrupted in our simulation based on these decisions. All these values were found upon through the position, velocity, and acceleration analysis, respectively. Later, I then followed and found the point of the S attached to the coupler link by following the position trajectory equations and solving for XS and YS. These are the results that I obtained. Later, after calculating everything on paper, I went ahead and built a simulation on SolidWorks design, and I acquired the graphs for the velocity, acceleration, and as well as position of the crank mechanism. I then later also designed a piston assembly showing the motion of the piston going full rotation with no interruption, as well as the slider crank mechanism that we designed.
For the 4-bar synthesis, we were given 3 positions, A1, B1, A2, B2, and A3, B3 for the coupler to pass through. To finalize the synthesis, we needed to find the pole positions, A0 and B0. To do this, we used the pole position equations, and we found the values. With those values, we were able to determine the link lengths R1, R2, R3, and R4, as well as theta 1, which is the displacement angle of link length R1. With that all determined, we were able to design a 4-bar mechanism in SolidWorks to show this fluid motion of the 4-bar mechanism, as you can see here. And in SolidWorks, we were able to show the position of A1 throughout the total motion.
As stated before, future applications are endless, whether it be in the automotive industry or the RC industry, which is also very large. It can go from steering components to suspension components, or even in the aviation industry, it could be used to design certain parts that would make the overall design more efficient. A very common, or more recent application is the automotive industry is using them for more efficient braking, where a motor would cause a linear displacement of an air dam, causing the drag to go up and the braking distance to go down.
In conclusion, the analysis and animation of the slider crank mechanism, as well as the synthesis of a 4-bar mechanism, was all a success. Our calculations matched with our simulations, which then showed us that we had full rotation without any disruption or bucketing. Continuous trial and error was inevitable in both slider crank and 4-bar mechanisms. We did so in order to perfect our calculations so that they would match hand in hand with our simulation values. We also found new adaptations of the slider crank and 4-bar mechanisms, which were discovered by Maciel, as examples of air damping braking systems, as well as future applications that can be used for prosthetic implementations. These are all the references that we use for our research. Thank you very much for taking your time and seeing our presentation.